Hello dear students. In last lecture we have studied about the event detection in an ECG signal, and in this lecture we'll continue that for the EEG signals. So in EEG signal, as we know, there are different rhythms, waves and transients. So this figure shows typical manifestations of the different activities. Basically, you can see these are the different channels. As we have seen in EEG recording, we have number of electrodes we are keeping at different locations on the scalp surface. So these are the different, you can say, positions and the waveforms we are obtaining from the different positions on the scalp surface. So there are different parameters or different kind of waves in the EEG signal. So we'll discuss some of them. In that we have K complex. So this is a transient complex waveform with slow waves, sometimes associated with sharp components and often followed by 14 Hz waves. It occurs spontaneously or in response to a sudden stimulus during sleep with an amplitude of about 200 microvolts. Then we have lambda waves. These are monophasic, positive, sharp waves that occur in the occipital location with an amplitude of less than 50 microvolts. They are related to eye movement and are associated with visual exploration. Then we have mu rhythm. This rhythm appears as a group of waves in the frequency range of 7 to 11 Hz with an accurate or comb shape in the central location. The mu rhythm usually has an amplitude of less than 50 microvolt and is blocked or attenuated by contralateral movement, thought of movement, readiness to move, or tactile stimulation. Then we have spike. A spike is defined as a transient with a pointed peak having a duration in the range of 20 to 30 milliseconds. We have a sharp wave that is also a transient with a pointed peak but with a longer duration than a spike, and it is in the range of 70 to 200 milliseconds. We can have spike and wave rhythm, a sequence of surface negative slow waves in the frequency range of 2.5 to 3.5 Hz and having a spike associated with each wave is referred to as a spike and wave rhythm. There could be several spikes of amplitude up to 1000 microvolt in each complex, in which the rhythm is called a poly spike and wave complex. Then we can have a sleep spindle. This is an episodic rhythm at about 14 Hz and of amplitude around 50 microvolt, occurring maximally over the fronto-central regions during certain stages of sleep. A spindle is defined in general as a short sequence of monomorphic waves having a fusiform appearance. Then we can have a vertex sharp transient, or we can also call it as a V wave. This wave is a sharp potential that is maximal at the vertex at about 300 microvolt and is negative in relation to the EEG in other areas. It occurs spontaneously during sleep or in response to a sensory stimulus during sleep, or wakefulness. In addition, the term burst is used to indicate a phenomena composed of two or more waves that are different from the principal, or we can say background activity, in terms of amplitude, frequency, or waveform. A burst is abrupt and has a relatively short duration. Now we can describe the EEG record in terms of the most persistent rhythm, that is the alpha rhythm, the presence of other rhythmic features such as delta, theta, and beta. There can be discrete features of relatively long duration, such as an episode of spike and wave activity. Also, there can be discrete features of relatively short duration, such as isolated spikes or sharp waves. The activity remaining when all the previous features have been described referred to as the background activity. And artifacts, if any, they give rise to ambiguity in interpretation. Now let's see the detection of different parameters, and in first we will see the presence of alpha rhythm in an EEG channel and how that method can be extended to detect the presence of same rhythm simultaneously in two EEG channels. So the two signals can be compared to detect the common characteristics via their dot product. As you can see in equation number 1, that is x dot y can be given as summation n running from 0 to n minus 1, the product of xn and yn. Here the signals xn and yn each have n samples. The dot product may be normalized by the geometric mean of the energies of the two signals to obtain the correlation coefficient. So you can see we have normalized by dividing it with, you can see the square root of whole square root of, we can say, product of two summations, or we can say two energies. These are of different signals like x and y. Now in case of two continuous time signals, like suppose xt and yt, the project of one signal onto the other, that is again the dot product, can be realized. You can see in equation number 3, instead of summation you will have integration running from minus infinity to plus infinity, and this is represented as theta xy. Now if there is any shift or a time delay in the occurrence of the epoch of present in the two signals, then it is necessary to introduce a time shift parameter to compute the projection for every possible position of overlap. The cross-correlation function between two signals of interest for a shift or delay of tau seconds, or we can say the k samples, can be obtained as you can see in equation number 4 and 5. So equation number 4 shows for the continuous case when we are considering the time shift or delay of tau seconds. So you can see in this equation we have introduced a time delay in one sample, that is yt plus tau, and in discrete case if you see we have the delay of k samples. The range n, that depends on the range of available overlapped data. Now when the autocorrelation function or the cross-correlation function have to be computed for various shifts, we can add zeros to one of the signal and increase its length by the maximum shift of interest. Further, in case of random signals, we need to take the expectation or sample average of the outer product of the vectors formed by the available samples of the signal. So here we have considered xn. It is a vector of xn, xi minus 1 up to, we can say, x of n minus, in bracket if I keep n minus 1 number of samples. Similarly for yn. So these represent the n-dimensional vectorial form of the two signals xn and yn with the most recent n samples being available in each signal at the time instant, let's suppose small n. Now, if xn and yn are simple observations of the random process, so their cross correlation function can be taken as, you can see we have introduced now the expectation operator, so xn into y transpose n, this t is for transpose. The outer product, that is n cross n matrix, it provides the cross terms including all possible delays within the duration of the signals. For autocorrelation function, all the equations mentioned may be modified by replacing the second signal y with the first signal x. So that means now we are computing or correlating with the signal with itself. So this x is then compared with itself. The autocorrelation function displays peaks at intervals corresponding to the period of any periodic or repetitive pattern present in the signal. So this property facilitates the detection of rhythms in EEG signals. The autocorrelation function of most signals decays and reaches negligible values after delays of a few milliseconds, except for periodic signals for which it will show or it will exhibit periodic peaks. And the cross correlation function displays peaks at the period of any periodic pattern present in both of the signals being analyzed. So the cross correlation function may be used to detect common rhythms present between the two signals, like between the two channels of the EEG. Now let's see some illustrations. So this is a signal we have taken from the P4 channel of the EEG signal, and here we are taking this interval of 4.67 to 5.81 second, this window. So when we compute the autocorrelation of this, you can see we have the periodic peaks. So this peak, this autocorrelation function basically displays peak at time delay of 0.11 second and its integral multiples. So if you compute the power spectral density, which is the Fourier transform of this autocorrelation function, so it can show the inverse, you can say, of this delay is 9 Hz. So frequency is 9 Hz. So which is within the alpha rhythm range. That means it is obvious that the analyzed signal segment contains the alpha rhythm. Now let's look at another illustration. So this is a signal which is obtained from the F3 channel, and again we are taking this window of 4.2 to 4.96 second, and this there is no alpha rhythm. So if you compute this autocorrelation, you can see there is no peak. That means no peak in the range of 0.08 to 0.14, indicating the absence of alpha rhythm in this second, or we can say in this segment. So this can also be predicted using power spectral density. You can see there is no alpha rhythm in the present in this. Now let's have another illustration. So consider here the two different channels, that is P3 and P4. If you see, both are showing the alpha activity. So we are taking the window of, you can say, 4.72 to 5.71 second. So now as this is the two functions, so you have to compute the cross correlation. If you see, it again shows the multiple peaks, and that depends on the alpha rhythm. As we can see, it is at 0.11 second, it is showing the first peak. So that means if you compute the cross spectral density for this, it will show the peak again at 9 Hz. That show that it is having alpha rhythm, means alpha rhythm is present in both the signals. Now let's consider another case, considering the signals from C4 and O2 channel of the EEG. In this, you can see one is having alpha rhythm and other is not having. So we have taken this interval of 5.71 to 6.78 seconds. So they are showing some peaks, but not that much relevant, as we have seen when the signals, or we can say both the signals, was having alpha activity. So that says that in this only one signal is having alpha activity. Now we have another case, that is signal we have taken from F3 and F4 channel, and if we see that there is no alpha activity in any of the channel, and we have considered the case of this interval 4.13 to 4.96 seconds when neither of the channel is having alpha rhythm. This can also be seen if you compute this cross correlation function, as there is no peak, that means there is no alpha activity present. So the relative strengths of the peak in the alpha range show the joint presence, singular presence or absence of the alpha rhythm in the various segments that are analyzed. So this was the detection of alpha rhythm. Now next is the case of detection for spike and wave complexes in the EEG signal. So to detect the spike and wave complexes in an EEG signal, we are assuming a sample segment, that is, we are considering a template of a spike and wave complex. As we mentioned that a spike and wave complex is a well-defined event in an EEG signal. The complex is composed of a sharp spike followed by a wave with a frequency of about 3 Hz. The template may be correlated with the same channel from which it was extracted to detect similar events that appear at a later time, or with another channel to search for similar events. A simple threshold on the result gives time instance where the events appear. So let's see one illustration for this. So this is a signal obtained from C3 channel of the EEG recording. So the spike and wave complex, you can see it is between 0.60 second and 0.82 second in the selected to is basically we are selecting in this range to use as a template. So one we have to use as a template. So we have chosen this interval spike and wave complex between 0.60 to 82 second in the signal to be used as a template. Now the template matching was performed with the same channel using the equation, that is normalized correlation coefficient. We can compute using this equation. So that is Rxyk, because we are taking one as a template, other is a signal. So that is kind of cross correlation. So you can obtain using this equation. Again, you are computing the correlation and then you are dividing by the power, square root of the power of the individual, you can say, template and the signal. The result demonstrates strong and clear peaks at each occurrence of, you can see, the spike and wave complex in the EEG signal. The peaks occur at the same instance of time as the corresponding spike and wave complexes. You can compare the two. Let's suppose here we have zero point 0.2, then we have this at around 0.6, or you can have at 1. So you can check here that we have the corresponding spike and wave peaks. Now another example. So here is a signal from F3 channel, and again we can compute the correlation between this and a template, and for this the same template we have used whatever we have mentioned in the last example, that is in the range of 0.60 to 0.82 second, and the result shows that the F3 channel has spike and wave activity complexes that match the template. So this was all in this lecture. So in this we have studied the detection of alpha rhythm as well as the spike and wave complexes in an EEG signal. For these topics, you can refer to the book by Rangaraj M. Rangayan, that is Biomedical Signal Analysis, a Case Study Approach. So for now,